Welcome back, students. In this video, I would like to talk about signed integers. So the question is, how do we represent signed integers in binary? Since the early days of computing, people have thought about different ways of representing a signed integer. One choice is to use sign magnitude. A second possibility is to use 1's complement, and the third possibility is the 2's complement representation. So these are three different ways of representing a signed integer. The idea is to divide the range into two parts. The first part will correspond to the numbers that are greater than or equal to 0. And the second part will be the negative numbers that are strictly less than 0. So half of these values will be greater than or equal to 0, and the second half will be negative. Today, modern computer systems use the 2's complement representation to represent signed integers. The 2's complement representation has many advantages over sign magnitude and the 1's complement. But let me first talk about sign magnitude and the 1's complement before coming back to the 2's complement representation. Okay, so what is sign magnitude representation? So given a number that consists of n bits, the most significant bit is known as the sign bit, and the least significant n-1 bits are called the magnitude. It's very simple. The most significant bit is the sign, and the remaining bits are the magnitude. If we use n-1 bits to represent the magnitude, then you can say then the largest magnitude will be 2 to the power n minus 1 minus 1. Okay, very simple. You can actually have 2 to the power n minus 1 magnitudes starting at 0, and the largest magnitude will be 2 to the power n minus 1 minus 1 because we are using n minus 1 bits to represent the magnitude. For example, if n is equal to 8 bits, so this is n, which is equal to 8 bits, you can have 2 to the power 7 possible magnitudes starting at 0 and ending at 127. If I would like to represent the number 45 plus 45, then the sign will be 0 and the magnitude will be 45. So this is plus and this is 45. If I would like to represent the number minus 45, then the sign bit will be 1, so that's actually minus, and the magnitude will also be 45. So this is negative 45. This is the concept of sign magnitude representation. What are the properties of sign magnitude? First, we have a symmetric range of represented values. If you use n bits to store a sign magnitude number, for example, inside a computer system, you have registers. Inside the CPU, we have registers. If you use an n-bit register to store a sign magnitude number, then you can go from negative 2 to the power n minus 1 minus 1 to positive 2 to the power n minus 1 minus 1. Notice that this is the largest magnitude. 2 to the power n minus 1 minus 1 is the largest magnitude. So for example, if just n equal to 8 bits, if we restrict n to 8 bits, then the range will be from negative 127 to plus 127. What's the problem of sign magnitude? It's very simple. So why people don't use sign magnitude? One problem is that we have two representations for 0. We have plus 0 and we have minus 0 because the sign bit can be plus or minus. It can be 0 or 1. And this is not good because we have two different representations for 0. Another problem is that it complicates the implementation of the addition and subtraction circuit. So we need two circuits. We need one circuit for addition and I need another circuit for subtraction. I have to examine the sign bit before deciding whether to do addition or subtraction. And this adds a cost and complicates the implementation of the circuit. So let me talk about this point specifically in the next slide. So suppose I would like to implement a circuit that does addition and subtraction of numbers that are represented in sign magnitude. I have to take into consideration the sign of the first number A. I have to take into account the sign of the second number, which is B. And I have to look at the operation, which is either addition or subtraction. So we have 8 cases in total. A can be positive, it can have a plus sign, or it can be negative, it can have a negative sign. The same thing for B, it can have a positive sign, or B can have a negative sign. Finally, the operation itself can be add or subtract. So if you look at all of these cases, we have 8 cases in total. So we have to design a circuit that examines the sign bit of A, that examines the sign bit of B, and it has to look at the operation, whether it's addition or subtraction. And it has to do the operation accordingly. So for example, if A is positive and B is positive, let us take a look at the first case here. So both A and B are positive. Then we can simply add the magnitudes of A and B, and we can say that the sign is positive. So this is a simple case. What about if A is positive and B is negative? The second case, if A is positive and B is negative, then we have to convert addition into subtraction. So if I'm adding two numbers that have different signs, I have to subtract. And in this case, we have even two different cases because A can be greater than or equal to B, or A can be less than B. So we have two cases to consider. If A is greater than or equal to B, we have to compute A minus B, and we can say that the sign is positive. And if A is less than B, then we have to compute B minus A, and we can say that the sign is negative. So you can see that this complicates the implementation because we have to compare the magnitude of A with the magnitude of B. The same thing can be said when I would like to add negative A to positive B. This is the third case here. So we can get negative A minus B, or we can get positive B minus A. If I would like to add two negative numbers, which is shown here, if I would like to add two negative numbers, then this is easy. Because both have the same sign, I can simply add the magnitudes, A plus B, and I can say that the final sign is negative. So this is an easy case. If I would like to subtract two positive numbers, like in this case here, then we have to check whether the magnitude of A is greater than or equal to B, or A is less than B. So we end up with two different results. Either it is positive A minus B, or it is negative B minus A, and so on. Let us take a look at the sixth case, which is positive A minus negative B. Now, this is an easy case because minus negative B is the same thing as plus positive B. So the result will be positive, and we can simply add the magnitudes. So this is the complication, okay, for sign magnitude. We have to examine the sign of A, the sign of B, and we have to look at the operation. And for this reason, people don't use sign magnitude because it complicates the implementation of the circuit. Next, I need to talk about the ones complement representation. So given a number A, it's given in binary, the meaning of the ones complement, it is obtained by inverting each bit of A. So for example, if this is A, let me just write A here. Okay, if this is A, then this will be the ones complement of A. I'm going just to write here A prime. And A prime is obtained by complementing each bit of A. That's the idea of the ones complement. It's a very simple idea. So now if you say that, okay, suppose I have a number A and I have the ones complement of A. If I want to add A plus the ones complement of A, which is A prime, let me write A prime here. So what is a plus a prime? If you add a plus a prime, you get ones, because if you add a 1 with its complement, which is 0, or a 0 with a 1, you get all ones. So if a bit in a is equal to a 1, then the complement will be 0, right? And if it is a 0, then the complement will be 1. So basically, if you add a plus a prime, you get all the bits are equal to 1s. So you say, okay, what is the unsigned value if all the bits are equal to 1s? It will be 2 to the power n minus 1, because we are using n bits to represent the number. So that's a plus a prime. Remember that a plus a prime is equal to 2 to the power n minus 1. What's the range of values that you can represent with 1's complement? Is the same as the range of value that you can represent with sign magnitude. Because half of these numbers will be negative and the other half will be greater than or equal to 0. For example, if n is equal to 8, then the range will be from negative 127 to plus 127. Now, one problem with the 1's complement is that it has two representations for 0. We have plus 0 and minus 0, and this is not good. We have seen this in the sign magnitude representation. It's also the case with the 1's complement representation. We have two representations for 0. Now, what is minus 0? Minus 0 is obtained by complementing all the zeros. So basically, you get all 1's. That is minus 0. And this is not good, okay? So we don't really need two representations for 0. I need only one representation for 0. The next topic will be about the 2's complement representation, but I talked about the 1's complement representation because it's an introduction to the 2's complement representation. So what is the 2's complement representation? It's the standard way to represent signed integers in computer systems. This is actually how computer systems today represent signed integers. A simple way to define the 2's complement is that the 2's complement of a given number, which is a, it's the 1's complement of a plus 1. That's very simple. You just have to add 1 to the 1's complement to obtain the 2's complement. This is why it's called the 2's complement, because it's the 1's complement by plus 1. That's it. So for example, if this is my binary number, this is a, then this is a prime, this is a prime plus 1. That's the 2's complement of a. So it's a prime plus 1. Now, if you add a plus the 2's complement of a, what do you get? So a plus the 2's complement of a, it's equal to a plus a prime plus 1. This is the 2's complement. We have seen that a plus a prime is 2 to the power n minus 1. And then if you add 1, you get 2 to the power n. So this is why a plus the 2's complement of a is equal to 2 to the power n. You can also say that the 2's complement of a is 2 to the power n minus a. Okay, that's the 2's complement of a. Here's a simple example for computing the 2's complement of a number. You start with a number, for example, plus 36. You can say that plus 36 is this number here in binary. The first step is to obtain the 1's complement of a. So this is a prime. So you invert all the bits. The 0 becomes a 1 and the 1 becomes a 0. And then step 2 is that you have to add plus 1. So you have to add plus 1 to a prime to obtain the 2's complement of a. So when you add plus 1, you might get a carry. So 1 plus 1 equal to a 0 and the carry. And then the carry plus 1 is a 0 and the carry. And then the carry plus the 0 is equal to a 1. And the remaining bits will be the same. Okay, these actually are the same thing in a prime. So this will be, this number here is negative 36. That's how we obtain negative 36. So we take plus 36, we take the ones complement of plus 36 by inverting all the bits, and then we add plus 1. Okay, so now that's how we obtain the, let me just, okay. So that's how we calculate the 2's complement of plus 36. What if I would like to take the 2's complement of negative 36? Do I get plus 36? The answer is yes. Yani you can do it backwards. You can start with negative 36. You can obtain the 1's complement of negative 36, and then you add 1, and this will take you back to plus 36. So if your number is negative, and you take the 2's complement of a negative number, this will give you the positive value of the number. So the 2's complement of negative 36 will be plus 36 as indicated here in this example. So if you start with the number a, which is plus 36, you take the 2's complement, this will give you negative 36. Now, if you take negative 36 and you take the 2's complement, this will take you back to plus 36. So the 2's complement of the 2's complement of a is simply equal to a. So the meaning of the 2's complement of a is the negative of a. There is another way to obtain the 2's complement. Okay, so the idea is very simple. If you would like to do it by quickly, what you do is that you look at the least significant one. So this one here is the least significant one. You skip the zeros until you encounter the least significant one. So these zeros are skipped here, and then you look for the least significant 1 bit. And what you do is you simply complement all the bits that appear to the left of the least significant one. So you keep the zeros and the 1 untouched, and then you complement all the bits that appear to the left of the least significant one. That's the idea of obtaining the 2's complement quickly without the need to compute the 1's complement plus 1. So that is another way to obtain the 2's complement. You can find this way is very useful and very easy. So this is plus, the first number is plus 36, and this is negative 36. If you take the 2's complement here of negative 36, if you take the 2's complement of negative 36, this will take you back to plus 36. You go back to the first number. So that's nice, okay? That's an easy way to obtain the 2's complement of a number without taking the 1's complement and adding 1. That is a quick way of obtaining the 2's complement. What are the properties of the 2's complement? Why people love to use 2's complement, or they use the 2's complement to represent signed integers? Well, if you look at the range of represented values, there are many reasons for this. Okay, let us first look at the range of represented values. First, we can represent the values from negative 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So for the positive range is the same. For the negative range, we have one negative value here, which is negative 2 to the power n minus 1. 2 to the power, negative 2 to the power n minus 1. So for example, if n is equal to 8, you can go from negative 128 to plus 127. So one of the advantages of the 2's complement is that there is only one 0, which is represented by all 0 bits. The meaning of the 2's complement is the negative of a. So when I take the 2's complement of a, it means it is the negative of a. If you take the sum of a plus the 2's complement of a, you get 0. This is great. That's what we need. So if this is minus a, the 2's complement of a is minus a. So a plus minus a, it must be 0. Now, you will obtain a carry, but this final carry is ignored in the case of the 2's complement representation. For example, suppose that my number a is given here, which is equal to 44. Then the 2's complement of a is equal to this number. So it's very easy. You can skip the least significant zeros until you encounter the least significant one, and then you complement all of these bits that appear to the left of this one. Okay, that's how you obtain the 2's complement of 44. This is negative 44. Okay, you can see that these are just the complement of these bits. So we skip the zeros until we encounter the least significant one, and we complemented the bits that appear to the left of the one. So this must be negative 44. So now if I take plus 44 and then I add to it minus 44, what do I get? I get all zeros and I get a carry, but this carry is ignored. This carry is equal to 2 to the power 8 or 2 to the power n. Okay, because n is equal to 8. So this final carry is ignored. It's not part of the representation. And you can see that my final sum is simply equal to 0. So this is plus 44. This is minus 44. And the result is 0. This is great. Okay, so therefore, if you take a and then you add to it the 2's complement of a, which is negative a, you should really get a 0. You will get a carry, but this carry is ignored. So now if I would like to look at 8-bit binary numbers, I will have 256 possible values, which are listed in this table. So you start with 8 zeros until you go all the way to 8 ones. The unsigned value will go from 0 to 255. These are the 256 possible values that you can represent in binary. So if these 8-bit binary numbers are unsigned, their decimal values will be from 0 to 255. These are the decimal values if you look at these numbers to be unsigned. If you look at the same binary numbers to be signed, you can give two meanings to these binary numbers. If you look at them as being signed, then the first half will be the positive numbers from 0 to plus 127. You can see that they are exactly identical to the unsigned value. So these are the positive signed values, and the remaining ones are the negative signed integers. So we go here from negative 128 to negative 1. Notice that if you pick any number here, okay, any number which is, if the most significant bit is 1, you can tell that the number is negative, but it's not signed magnitude, it's in the 2's complement representation. So how do you obtain the decimal value of a negative number if you have the number represented in the 2's complement representation? This is simple. Let me show you how this is done. Now we know that the signed value is the unsigned value minus 2 to the power n, as we have seen in a previous slide. And the reason why it is the case is that we have seen that's how we obtain the 2's complement. Okay, so you can always relate the signed and unsigned value. For example, if I take this number here, which is in binary, its unsigned value is 128, but then if you say minus 2 to the power 8, which is 256, you will get negative 128. If you look at this number here, it will have the value 255 if this number is unsigned. But if you would like to find the signed value, you have to say minus 256. So 255 minus 256, it will give you minus 1. So that's one way to obtain the signed value. Look at the unsigned value and then say minus 2 to the power n. N in this case is equal to 8. So minus 2 to the power 8 means minus 256. That's one way to obtain the signed value of a binary number, okay, when it is represented in the 2's complement representation. Okay, that's the signed value. There is another way, is that you can say that, okay, pick any number. Okay, so you can say that given any negative number. So the most significant bit is this sign, and it's a weighted, it has a weight. So for example, if we are using 8 bits, then the weight of the sign bit will be negative. It will be, for example, if we are using 8 bits, then the weight of the sign bit will be negative 128. The remaining weights are exactly the same. So for example, this one will be 4, this one will be 16, and this one here will be 32. So if you add 4 plus 16 plus 32, and because the number is negative, you add negative 128, you get negative 76. So this number here must be negative, and its decimal value is negative 76. Notice that this is not really sign magnitude, because if it was sign magnitude, it will have a different value. So this is 2's complement representation, and the decimal value of this number will be negative 76. So we say that the weight of the sign bit is negative, and the weights of all the remaining ones are positive. If the sign bit was 0, it will be 4 plus 16, which is 20, plus 32. This will give me 52, okay? So notice that if the sign bit is equal to 0, you get 52. If the sign bit is 1, you get negative 76. You don't really get negative 52 because this is not sign magnitude. This is the difference between the 2's complement and the sign magnitude representation. So we have to add 52 minus 128. This will give me negative 76. That's a quick way to obtain the decimal value of a signed number when it is represented in the 2's complement representation. Now, this slide summarizes the differences between sign magnitude 1's complement, 2's complement, and there is a column here that shows the unsigned value. So this is for 8-bit binary numbers. You can give 4 different meanings for the 8-bit numbers. If the number is unsigned, you can go from 0 to 255. So there is no sign. If you have sign magnitude, you can go from plus 0 to plus 127, and you can go from negative 0 to negative 127. Notice that there is plus 0 and there is negative 0. So that's it. You have, this is a, you give a different meaning and a different value for the number when it is represented in sign magnitude. If it is in 1's complement representation, so if these binary numbers are in 1's complement, notice that the first 128 values are identical. Against plus 0 to plus 127, there is no difference between unsigned, sign magnitude, 1's complement, and 2's complement if the numbers are positive or 0. The difference is in the negative values. So in the case of the 1's complement, notice that if this is plus 127, then this must be negative 127. Notice that if this is plus 126, this must be negative 126, and so on. So you can see that the decimal value of the number is different when it is represented in sign magnitude 1's complement or 2's complement. Already we have seen the 2's complement value in the last slide. So that's it about this video. Okay, so we have seen signed integers in this video. In the next video, I will talk about addition and subtraction of signed numbers that are represented in the 2's complement representation. Thank you for watching.